Hi, I'm going to make some brief remarks. Well, first of all, we're really pleased that our first KITP colloquium of 2014 is going to be given by Philip Kim. Philip Kim is a professor at Columbia, and I can roughly go through his history. He's from Korea. He did his undergraduate at Seoul National University. Then he moved to Harvard for his PhD with Charles Lieber. And then after getting his PhD, he did a Miller Fellowship at Berkeley. And in 2002, he went to Columbia, and he's been there for 12 years now, entering his 13th year at Columbia. Philip Kim's very famous, in a sense, for his work on low-dimensional transport in quantum transport. And as many of you know, quantum properties in 1- and 2-dimensional systems are different than in 3-dimensional systems in some ways. I'll just point out that many people in the know feel that the 2010 Nobel Prize was missing one name, which was Philip Kim's name. And in fact, this has been pointed out in many places, even by the Nobel Prize winners themselves, who acknowledged Philip's work and said they would be quite happy to have shared the 2010 Nobel Prize with Philip. So before I introduce Philip, we're also lucky to have Douglas Hofstadter here at UCSB this week, and he'd like to say a few words.
Well, I had the pleasure of giving a departmental colloquium yesterday describing work that I did when I called it Musings and Reminiscences of a ex-quasi-physicist. I never really was a physicist, but I managed to stumble on a beautiful graph which had a fractal nature, although the concept of fractals hadn't yet been introduced by Mandelbrot, so the word didn't exist. But anyway, I was lucky to do that. Now, some years ago, I was in Petersburg, and I arranged to give a talk on rather elementary geometry at a Steklov Mathematical Institute, and there were a handful of mathematicians in the audience, and they didn't seem very impressed by what I said. And then one of them took me out to go see a different institute there, the Euler Institute that he was associated with. We were just sitting around having tea, and he was saying, "I really admire your father's work in physics." Well, you know, I mean, my father was a famous physicist, and so I took for granted what he was saying. And then he said that beautiful fractal thing. And I said, "That was me." And then he looked at me with astonishment and he said, "Oh, then you are a very important person." That was hilarious. So anyway, this is my one skirmish with physics was that way back in the 70s, and I came out with this article in 1976. I had done the work a couple of years earlier, and in the article I speculated about whether or not the ideas that I had found, this fractal nature of the spectrum, could ever be tested, because it seemed to require magnetic fields that were of a magnitude that was unreachable, way out of the limits of the current technology. But there were some thoughts that other people had suggested about making artificial lattices. But I don't think that any such thing was really done with any success until very recently. And Philip was the key person who did this in graphene, and so he's going to elucidate these ideas, and I will learn something about how my ideas were found or confirmed in some sense roughly 40 years after I found them.
Okay, thank you. Thanks for the nice introduction. I'm not sure whether that is official comments from the Andre Geim, but anyways, I'll take that as a compliment. Thank you. Yeah. So I have the really, really daunting task today, right? Because I don't know how many of you actually heard yesterday's the excellent colloquiums, right? Rely on just the two transparency, not even computers, and then delivers beautiful concepts that today's talk is based on. I think there's no way that I can kind of outphase that the colloquiums. And also think about it. You just talk about the Hofstadter's butterfly in front of Hofstadter. I think that's also kind of very, very daunting. Well, I would take that it's better than just to talk about the Bloch or Landau or the Dirac in front of Bloch, Landau, and Dirac. But so it's kind of challenging. All right. So as Doug mentioned, the phenomena, what you call this, the Hofstadter's butterfly or the Hofstadter's fractal, like the energy spectrum, becomes quite, I would say, revived quite recently. Recently means it's actually less than a year. Experiment has been going on in many places for probably over 30 years or 40 years of the time. But the real evidence, or that kind of decisive evidence, I would say, is that kind of pops up quite recently. And it's actually not only just my group, but also about the same time, only kind of few days or few weeks of the difference in terms of the publication, actually pops up in 3 different groups, reporting very similar things. My group at Columbia with other collaborations, Andre Geim's group at the Manchester's, Pablo Herrera's group at the MIT, they basically kind of report very similar things that observe into graphene, make some of the superlattice I'm going to talk about. But not only this, actually, only a few months after this one, and there's a report coming from also the cold atom communities, like the people just can make this optical, the lattice, the cold atom sits in there, and the people start to see that very similar spectrums, or very similar physics that I'm going to discuss, or which actually was discussed yesterday. So what I'm going to do is basically I will focus on this kind of bit of narrow scopes and then try to deliver some of this experimental evidence, what I believe the experimental evidence of seeing these fractal spectrums. I want to actually start with the ethnology of my team. My team is a relatively large team, consists of quite interdisciplinary groups, not only one group, but kind of few groups together, be theories and experiments and then material preparations and various things. So I don't want to go over all the details, but Corey Dean now moved into the CUNY, is the main guy who actually carry out the most of the experiments and then also kind of deeply into the analysis and so on. But actually, all of the team actually had quite good time and interesting time to learn about this relatively old physics, but in the kind of new light. Okay, so let me start with kind of really back and kind of beginning. I want to kind of start with the Bloch. Well, Felix Bloch, we know about this kind of basically initiator of, I would say, condensed matter physics in some sense, quantum condensed matter physics. They're developing these band structures based on the Bloch theorems and so on. It turns out the Bloch's paper that proved that this Bloch theorem is published only probably about 2 or 3 years after that Schrödinger wrote his seminal paper about the Schrödinger equations. Right? So you can imagine that back then in 20s, how the field is evolving, that after that you just kind of get the Schrödinger equations, you want to use this hammer to kind of hit the many, many things. And Bloch is basically hitting this, whether we can describe the electron dynamics in the periodic lattice, which is a kind of crystals model, right? And then famous Bloch's equations and the Bloch's wave functions consist of. Important part of that is if you just look at the energy spectrum of this Bloch wave functions, turns out the energy spectrum is not continuous anymore. The free electron-like energy dispersion should break down into this band-like form. In other words, there are certain place of the energy, there is a gapped out, so there is no states that are allowed within this gap. Moreover, if you just consider the periodicity, you can just fold this band into the so-called Brillouin zone, describing this periodicity. So that now you just have the finite number of the electron per unit cell. Then basically you feed up this band up to the certain levels. Now, if the atoms in the unit cell donate the sum of the integer number of the electron, which is usually the case, right? Then usually band becomes half filled or fully filled, right? Especially when band is a fully filled, it's an interesting case that now energy spectrum is the gapped, meaning that there's no excitations in the low energies possible and turn into insulator or semiconductors and that idea, right? This gapped structure is quite important part of this talk, right? Now, in this kind of this band gap idea is a kind of profound, and we can categorize metal, insulator, semiconductor just based on this kind of gap, right? But once you just look at the gap, there's another interesting the quantity we can exactly extract. If the Fermi energy is in the gap, that there's integer number associated with that, meaning that how many bands got filled up here. It's actually associated with how many electrons per unit cell, right? There's a way that you can actually extract this number of the filled band just looking at thermodynamic quantities, such as electron density at the Fermi energy. If you just think about that, if there's a density of the electron up to this Fermi energies, if I know these functions, basically taking the derivative of this density with the unit cell volume and normalized it to make the dimensionless quantity, this becomes an integer. And this integer number is nothing but just how many bands got filled up. It's simply because there's periodic boundary conditions in these structures, right? So anyway, so there's always kind of one important integer number associated with it when you have the Bloch band and your energy is within the gap, right? Now, the other names that I put in the title is Landau. Now, about the same time, probably 1 or 2 years later of this Felix Bloch's kind of seminal work, what Landau worked on just solving Schrödinger equation is well known that problems now is just kind of solving that how the electron moves under constant magnetic field. And of course, this solution we all know from the elementary quantum physics is basically quantized classical cyclotron orbits, such that each orbit contains one flux quanta, or the integer number of the flux quanta defined by this fundamental constant of the physics, right? So that's basically the solution, simple solution. Now, if you just apply these Landau solutions in two-dimensional system, two-dimensional metallic system, free electron gases, they're interesting enough that originally this continuous density of state in the two-dimensional electron in the two dimension start to break up into the set of these levels that defined by this kind of the Landau quantizations and kind of look like harmonic oscillator forms. Because you shoved into this continuous density of state in the few discrete levels, you can imagine that each of the levels should be degenerated quite heavily. In fact, you can actually count number of the degeneracy per levels by just looking at that how many of these quantized orbits, cyclotron orbits, you can put into the system. Basically, it's again counting problems, right? Now, very similar things we did at the inter-Bloch case, we can just do that. What if my Fermi level is within, between this Landau level, so such that I have the gapped system? And then we can just do the same, the exercise. We can just count the number of the levels that filled up, which is integer number, right? But this integer number can be easily computed because I know that how many, in principle, the degeneracy there, basically how many orbits can fit in there, which is related with the magnetic field, of course, right? And what is electron densities and so on. So this integer number, in other words, often we call the filling fractions of this Landau level, can be easily computed knowing that magnetic field or more, in other words, the magnetic length, the size of this quantized orbit to the density, you form this dimensionless number, and that's basically give us another important integer number, which we call the filling fraction nu. In fact, this filling fraction nu plays an extremely important role that when you study about the magnetotransport into the two-dimensional electron system, say quantum Moire effect and such a system, basically this is the number that we want to know, that I'm going to talk about a little bit more later, right? So now, going back to the, say, 30s, right? Now, if you are living in the 30s as a physicist, what is the problems you want to solve? Of course, I mean, you can just do the great things, but kind of something that you can, incremental thing you want to do is, well, what if we just combine these two problems together? Solving the problems, electrons under the constant magnetic field, but in periodic potential, right? Seems like that's the natural problems, but it was not a too easy problem. It took many years, about probably 20 more years, to actually really quantify into some quantified equations. That was one of the earlier work done by Harper. What Harper did is basically he break down into the problems in the rather simple forms. He tried to extract the essence. What he did is actually took these problems with constant magnetic field and periodic potentials, but simplest case you can imagine is, say, tight binding model in the square lattice. That's probably one of the simplest model we know how to solve that. And just try to solve these problems under any magnetic field, right? Quickly, you realize that in this case, magnetic field can be parameterized, say, such that if you just compute the magnetic flux per unit cell and probably normalize by the flux quanta, then this becomes a dimensionless number, and this Harper's, the Hamiltonian can be parameterized, and within the tight binding band, the description, you actually break down this, the Schrödinger equations in terms of the differential equations that are called Harper's equations. There's only one parameter, B, which is a dimensionless field that controls these equations. So now, equation is set. So the only thing is you just solve this equation and draw that what this energy level should look like. Now, if you go back to the Harper's original paper, which is published in the 50s, he himself actually expressed some of the enigmatic statement in this paper. If you just read it, well, he says, unfortunately, this seems very difficult to determine in detail, the spectrum, even for the sinusoidal potential. In other words, you just kind of think about just simple nearest neighbor hopping problems on the square lattice. It's difficult. And the reason is, well, level structure will consist of irregular groups regularly repeated. So this is quite an enigmatic statement, right? Something is irregular but irregularly spaced. And already that some hint of the problem is there. And you can quickly realize why that's the case. Because in some sense, here is a deeply rooted of the commensuration and incommensuration problem. In other words, this problem has a two different length scale. One is, of course, lattice length scale, which gives you the periodicity of the electric field. And the other one is, of course, the magnetic length scale, which also try to give its own periodicity in terms of magnetic orbits. And these two, the competition between these two length scale actually embed in these Harper's equations. And that makes some things quite unique and different. Well, there's a toy that's called the spirograph, right? And probably you played around in that when you're a child, or even now, right? This is basically that really reflect that this commensurability problems. Now, in this simple geometry, you can draw the many, many patterns by just kind of putting different wheels, right? Of course, this wheel has a tooth, and that number of the tooth is integer number, so they eventually, they can be commensurated. If you just rotate many, many times, it will come back in periodic structures. But if these numbers, and this the integer number of the tooth, is largely the coprime number, large coprime number, then basically the structure becomes more and more complicated. If you think about what if there is no commensuration, what if this ratio is irrational number, then you will see that there is no periodicity, right? And in fact, this is one way that you can create the fractal in the modern terms, right? And this simple toy already shows that the commensurability and incommensurability create quite unique and intriguing features that even for such kind of simple geometry. And that's basically what embedded in Harper's equations. It took another 20 years to actually get the kind of significant progress in this problem. And that's basically what Doug did in 70s. So what has been known by then, that many people actually try to attack this Harper's equation to look through these problems. And one thing you can just solve this problem relatively straightforward is when there's a two length scale commensurate each other. In other words, those kind of magnetic field is expressed in terms of the rational number with P over Q of two integer. Then basically what you can do is you can extend your unit cell, so-called this magnetic unit cell, such that within this large unit cells you form that integer number of the flux quantized getting through. Basically this problem can be solvable, and there's few bands appears. In fact, actually you can see that the Landau levels and the magnetic field will break down into the Q sub band because of those kind of the large magnetic unit cell you just put down. But the problem, as Doug actually mentioned yesterday, is basically there are so many infinitesimally close irrational numbers nearby this kind of any rational numbers. And this statement doesn't make too much of sense intuitively, right? And people actually didn't find out how we can attack this problem until that you see this spectrum, that what Doug actually plotted out using this old computers, HP computers, I heard, right? So this spectrum, which is a simple solutions of these Harper's equations, with probably using the large number of these P and Q coprime numbers, mimicking that more or less kind of close to irrational numbers, shows that how this kind of wealthy structure of the spectrum is there. It's called the G spectrum, G plot back then, but now actually calls the Hofstadter's butterfly. In some sense, you can see that, well, there is some wings there, butterflies there, and the butterfly wings, you can see there are other butterflies and so on. So there is some of the recursiveness, self-recursiveness is in there, and in modern languages, actually fractalness is in there, self-similarities. In fact, this diagram is so famous now. Part of the reason is because this is only a few examples that you can still find out quantum fractal. You solve the quantum mechanical problems and you get the fractal, and this is kind of one of the few examples that you can meet there. Probably the first example present in that way too. Now, this is a very interesting story that I learned yesterday, although I actually kind of suspicious a little bit on this one. It's only kind of sort of the papers after over his graduate work, but there's no the advisor's names in there. So typically, that's not the typical case in the modern physics department that you just write some important work as a PhD. You want to actually include the advisors. He's not there. Doc's advisor was Wannier, that we all know of the Wannier of the Wannier functions or many other things. Why he's not in there, I think probably any of you that were in the yesterday talk that you know that's the reason. Now, what happened on this one is, okay, so this is a really fractal, and it's complicated. But we want to do a little bit more than just complicated. Since Doc left after showing this the spectrum, somebody should carry on the work to analyze the something behind of the spectrum. Who was it? That was actually Wannier. And eventually convinced enough that this is important work, and he tried to analyze what is the structure behind of this fractal pattern. Now, that's not too easy. Now, I just kind of show this spectrums, the kind of 90-degree rotation. So this is energy, and this is magnetic flux normalized. You can read it following way, right? So in the low enough magnetic field like this, zero magnetic field, of course, there you have the continuous band. Remember, this is a square lattice with tight binding model. So I have just one tight binding model. It's a band bottom and band edges, and then there's a continuous spectrums there. Now, when you turn on the magnetic field, suddenly states start to appear. Something's from the bottom and something's from the top. Now, this view, you can view that where I just increase the magnetic field, and there's a Landau level start to develop, and each of the band edges. So this is electron like the Landau level, and this is a hole like the Landau level. You can call it in this way. And of course, when the magnetic field becomes larger and larger, what you expect to see is basically the cyclotron orbit becomes smaller and smaller, and the electrons start to see that lattice structures nearby, which actually start to disturb this Landau level. So you can view that, well, this is a Landau level, but eventually that this lattice structure starts to disturb the Landau levels, break this degeneracy in the Landau level, and create these beautiful structures based on this disturbance coming from the periodic lattice. And same thing for all this higher Landau level. Now, once you just kind of realize this, and it was a 1 year's really kind of work that realized that instead of you just focus on this spectrum as states, what if you just focus on the gap in between the spectrum? Now, if you just look at this side of gap, right, this is basically a gap between first Landau level and second Landau level here and the breakdown. But whatever this degeneracy break it down the states, number of the state here should be the same as number of state that you just start with in some sense, right? So if you just do that, if I stay on the gap, and if you are interested in not only the energies, but how about the number of the electron below this gapped region as a function of magnetic field to fill up these states, and then you can actually do the following things. Well, basically along this gap, along this state, which is coming from the first Landau levels, basically, if I just plot it out, density versus the magnetic field, because it's basically the same as the Landau level that you start with, you just draw the one line there, right? Okay, so line versus line is okay. But now if you just, there is some difference that if you start to follow through the second Landau level. So this is the second Landau level, that if you just try to do that, you have to be carefully count where actually second Landau level should go. And it's actually a bit kind of zigzagged and jagged way that you have to follow the second and third Landau levels and so on. But nevertheless, the point here is if you just plot in terms of the density versus flux that normalized by the density per unit cell, flux per the flux quanta, then becomes a line because it's same as a Landau level, just kind of density counting, basically, right? So you have some correspondence of this jagged line with the straight line there. Now you can do the same thing for this part, which is whole like the Landau level. You get the same languages like this, right? Now in this side, you see that this is a symmetric. In some sense, you can see that if I just put one flux quanta into the system, everything should reset in the tight binding model, right? So basically, in this spectrum, you can see that instead you have instead of the up magnetic field, you have the completely filled Landau levels, completely fill this unit cell with the flux quanta, and apply the magnetic field in opposite direction, right? So that's nothing but just kind of viewing that concept. So you can just do the same things the following way, right? So what you see here is a kind of beautiful duality between these structures to this set of the lines, right? Well, set of lines are boring, but there's an important part. All this slope is, in fact, and as well as the offset of all of this thing turn into the integer, simply because it's level counting problems, right? So what you see here is, again, in this spectrum, somehow there's integers that the embedded here, integer, in a sense, if I just draw this line, in terms of the equations, there is a so-called Diophantine equations, where the two integer appears. One is slope, and the other one is offset. Both of them described by this kind of the set of the lines, right? So in some sense, this Hofstadter spectrum contains a two integer number in it. Was not obvious in terms of the standard spectrum, but once you just kind of make the dual into the density with the flux, basically it's obvious. There is a two integer number that govern this set of the lines there. And that was Wannier's work, published 2 years after that Hofstadter's initial paper, showing that there's integers actually embedded in here. Up to here, it is rather mathematical. And I had a quite difficult time to swallow these papers to get to this kind of essence. But the part is, as an experimentalist, if it ends here, was probably kind of purely mathematical things. But what is interesting about the physics is this integer number come back to the physics, and not only just the theoretical physics, but give some things about the experimentalist. In other words, this two integer number carries a very important physical quantity. Well, that's one thing that I'm going to mention. But before that, one thing you notice that is there is some special part. There's a band is continuous. For example, half, 1/3, and 4th, 1/5 of this flux quanta. There's a number of the bands that appears. The number of the band is exactly the same as the denominator integers in the denominator. And that's what we call often the fractal band, meaning that it is itself is very continuous. But right after or right below that band, in terms of the flux, there's a maximal fractalization comes up. Basically, there's so many irrational numbers nearby, so number of the band there is enormously large, infinitely large there. And that's actually captured, again, so-called this, I call this Wannier diagram, the density versus flux diagram, appears as a kind of set of the lines. Right? So there's kind of this fractal band can be easily spotted in this type of the spectrum. Now, I mentioned that these two integer numbers, in fact, is related to some physical quantity. So what is it? First, this number S, which is offset of the line, is nothing but just how many bands got filled up. So if you just go back to the original idea that I just set it up for the block band, how many block band filled up, that's basically the same thing. If you just know the band here, how many bands got filled up, that's related with this S number, right? But how about the T, the slope of this line? And that comes actually quite interesting. Around this time, around the end of the 70s and beginning of the 80s, there's the big things happens in the experimental physics dealing with this low-dimensional electron system. So basically, quantum Moire effect was discovered in the 80s. And people were amazed by just kind of such a sample that you measure in the experiments that suddenly gives such a kind of nice plateau, quantized value that described by the integer number. And in fact, that whole conductivity, quantized whole conductivity, is related with the slope. And that was done by the earlier work of Streda around the 80s, and showing that, in fact, this T, that in the slope, is related with experimentally observable, which is the whole conductivity, meaning that this T is coming out the integer times of the E square of the H, the quantum conductance is whole conductivity, meaning that conductivity, whole conductivity should be quantized in this system. About the same time, Dowless and co-work actually show that not only this is the case, but also if you just express this whole conductivity in terms of wave functions, that this has an interesting expression. Back then it was not called as kind of deeply made with connection with the mathematics, but now this is called the kind of Chern number that associated with these wave functions under the magnetic field. So there's some topological meanings associated with this kind of the number that the slope T here, right? The point here is now, once you have this, the Hofstadter spectrums appears, now there's important experimental observations that we expect. Whenever there's a gap, whenever my energy is within the gap of this one of the fractal spectrum, what I expect is that whole conductivity is quantized, and that quantization comes as T, where when you get into dual, basically the slope of this line corresponding to that spectrum part will give you that whole conductivity. Which means that in spectrum, any wide range that I showed you, that you just pick up the line that corresponds to these wide ranges and pick up this integer number and assign the color for each integer, say red for the 1, blue for the -1s, and so on, then you can actually paint this butterfly in color. So now the butterfly acquires color and becomes more beautiful, right? And you will see that this type of the pictures if you Google this Hofstadter's butterfly everywhere. Because of this kind of beauty, many experimentalists after this try to catch the butterfly. But there is a big problem. Big problem is following. Now, to look at this spectrum, what you have to do is, of course, you have to increase the magnetic field up to here, certain levels, about order of the 1 of the flux quanta per unit cell, to get enough the breakdown of these Landau levels, right? So how high magnetic field do we need? Otherwise, basically, we'll kind of screen by disorder and temperature. Turns out, to reach certain magnetic field and their levels, because atomic lattice is about angstrom, you need probably well over the 10,000 Tesla of the magnetic field. It's many, many orders of magnitude larger than any human being can attain on the surface of the Earth, right? So this becomes quickly not even academic problem, it's a complete esoteric problems, unless there's some solutions happens. Now, Doug briefly mentioned about this paper, but actually before he mentioned, when we actually get into the paper, the original papers of the Hofstadter, already the solution was suggested here. If you just read it carefully, maybe you need the manufacturer's systematic synthetic two-dimensional lattice to realize that reduce down this artificial atomic lattice, that lattice size is not the angstrom, but something like, say, 80 or 100 nanometer length scale, then you get into the comfortable range of the Tesla to 10 Tesla, where the experiment can be done in the lab. Indeed, technology got evolved in past 30 years. Around the 90s, people know how to make these structures about 100 nanometers or below. And then people try to realize this Hofstadter's, the fractal spectrum in two-dimensional electron gas. And there are some of the earlier work that I just present here in many places in the world to try out to chasing these things and using this conventional two-dimensional electron gas between the semiconductor heterostructures. The result was kind of tantalizing. Many cases, if you just make the lattice, then basically you start to see the Landau levels that break down as a perturbation coming from the periodic lattice. And some cases, if you just carefully analyze those kind of breakdown, may actually mimic some of the spectrums that expect that initial Landau level breakdown to 3 groups, 4 groups, depends on the magnetic field, can be seen there. But in a sense, this is kind of indirect evidence, not showing that indeed there is a kind of real quantization is going on. The trouble of this problem is, of course, when you have this high quality two-dimensional electron gas, when you make this overhanging structures to give the periodic structure, often degraded electron gas underneath, so that you don't have the electron coherency or the ballisticity remains within this kind of the artificial lattice to mimic this atomic the lattice structures, artificial atomic lattice structures. So that was a problem, that was a status until probably a few years ago. Now, what happened in probably past 7 or 8 years is, of course, we know that graphene or other two-dimensional systems that pops up based on that kind of different efforts. Graphene was first discovered by the Manchester group in the 2004 by just kind of playing around with graphite with the scotch tapes, and then happened to you get the single atomic layer. But actually, that really revolutionized this low-dimensional system in some sense. With such a rudimentary technique, that you can get a fairly different system, electron system, with a very high quality. Now, graphene is quite special in some sense because its energy spectrum is very different from just a two-dimensional electron system. Typical electron system has electron mass, can be renormalized by the interaction with this, the periodic lattice. But in graphene, in fact, actually that goes extreme, such that instead of you have the massive electron like the spectrum, you have this linear spectrum where that the electron, like the hole, like the spectrum actually meet at one point. Seemingly, it's very similar to the Dirac, like the spectrum, or the quasi-relativistic spectrums of electron. In fact, not only just the analogies, if you just go through this tight binding model carefully and just kind of look in the detail, it turns out the Hamiltonian that described electron dynamics in this system, especially near this so-called charge energy point, is very analogous, or exactly analogous to the Dirac equation, original Dirac equation, except that speed of the light is replaced by the Fermi velocity in this system, which is about 300 times smaller than real speed of the light. And because of this linear dispersion relation, there's many, many things, exciting things appears in graphene. I don't want to go over all the details, but there's one important part associated with this problem, which is under the magnetic field, they develop the Landau level. Well, okay, that is expected. But because of linear dispersion relation, this Landau level actually is fairly different from just conventional system, especially if you look at the energy scale of this Landau level, especially if you stay in the low energy Landau levels. The separation between Landau level is much, much larger than what you expect to see in conventional two-dimensional system. Often this is about order of magnitude, even 2 orders of magnitude larger than conventional system, given the magnetic field you can obtain in the lab. So this huge Landau level separation is another asset that we can use to realize this, revisit the problem that I just mentioned in the beginning. Because we have at least one energy scale is fairly large. And very initially, that people just kind of make the device out of graphene and shows that indeed the graphene shows this quantum Moire effect. And this quantum Moire effect sequence is rather different from conventional systems simply because, again, the spectrums and so on. But again, I'm not going to go over in the details on this one for now. But that's another important ingredient. Now, such a rudimentary technique, you can get the sample, but still shows kind of nice quantum Moire effect. Now, the next problem that we have here is, okay, so we know that graphene can just produce now quantum Moire effect, Landau quantizations. Now, we want to actually now put the periodic potential there. I told you in the beginning that the two-dimensional electron system, you can get even higher quality, but when you actually put the artificial structures on there, you degraded the properties of the electron gas. Maybe same thing, similar things may happen to the graphene. And is there a way that we can avoid those degradations by just putting some of the artificial lattice? In fact, there is a solution for that, which actually given by the nature. Graphene is only one kind of materials that shows this layered system. There are many other kinds, or actually very similar systems do exist. One of the examples is boron nitride, where basically 2 carbon atoms in unit cell is replaced by the boron and nitrogen. As a result, on boron nitride, unlike the graphene, is a completely insulating system. Gap is huge. So it actually serves as a good substrate in some sense. And it's atomically flat, and all the chemical bond is within the layer, like the graphene. So when you put the graphene on the boron nitride, basically they don't talk to each other. But yet boron nitride can serve as a good substrate, support the graphene. So that's actually one interesting thing. Now, practically what you can do is basically in the lab, you can just get the graphene and boron nitride as single crystal. And our favorite technique is still Scotch taping. Just take the Scotch tape, one material, Scotch tape, another materials. It's a little bit more complicated Scotch taping, but essence is very similar. And then you just kind of put them together very closely under the microscope and just put on the one on the top of the other. And that's it. Then you get the, say, graphene on the top of the boron nitride. And then you can just make this device, basically design your electrode to contact this system and just see how the system looks like. Turns out if you just do that, graphene quality is even better than graphene sitting on any substrate. Part of the reason is basically boron nitride supplies fairly good substrate without a lot of the defects, and yet it's also atomically flat substrate. So it's in some sense a very ideal substrate we can use. But not only that, if you just look at the atomic length scale, there's some subtle things happens. Now in this procedure, you can see that since we are just doing this kind of Scotch taping, we don't have really atomic precision to control everything here, right? So naively you can think about if I just put the graphene on the boron nitride, if I just try really, really hard, probably I can put them on exactly on the top of that. It's really difficult. But even if you do that, there's a small changes, small difference in the lattice constant. So I cannot make them exactly commensurate each other, right? Now, even more, this is a really difficult to make it, but typically there is some angles of the twistings that by just kind of putting these two lattices each other. And if you just put kind of in the misfit angles, and then there's kind of complicated things happens, especially if you just think about the electron sitting in the graphene layer underlying the boron nitride, which is different atomic potentials, will give you quite complicated interaction potential. Although this is van der Waals interaction, so the magnitude is not too high, but nevertheless there are some modulations of things happens, right? But if you just kind of zoom out and kind of look from the outside, you can start to see that new patterns start to appear. So right here's some of the hexagon type of things appears. Here's the hexagon size is small, like this, and even smaller hexagon arrays and so on, and it becomes kind of some patterns appears, right? In fact, this is what we call the Moire patterns. When you have the two similar lattices stacked together with some small angle difference, there is the large scale of the superlattice modulation start to appears, and those superlattice potential, the wavelengths, strongly depends on these angles between them. In fact, you can even calculate it rather simply, and this is basically what this Moire pattern look like. Now, this is a very good tool in some sense. By just looking at this graphene on top of the boron nitride, in case if you just adjust the angle, basically you can create some of the superlattice structures whose lattice constant can be controlled in principle by just kind of choosing the right angle. In practice, basically we make many samples and we just choose right angle samples for our experiments. So this is not only the PowerPoint that the demonstration, but earlier work that the people use STM or AFM try to look at this graphene sitting on the boron nitride, and they start to see that all this kind of, here's atomic lattice, but on the top of the atomic lattice, you can see that this beautiful hexagonal lattice that coming from the Moire between graphene and boron nitride. STM work done in the Eva Andre group in the Ruckus, and then also done in the MIT group also shows this kind of beautiful Moires. Not only this Moire appears, when you do the spectroscopies, basically looking at the electron density of a state by just using spectroscopies, they start to see that this dip, which is correspond to the Dirac peak, Dirac point, low density of state. As you go through, some anomaly start to appear. In fact, why there is anomaly? Well, think about this Moire superlattice is the modulations or the perturbation on your periodic lattice. What you can do is basically, if you just kind of think about this is periodic perturbation, you just form another Bloch band, considering this larger perturbation, a larger unit cell as your kind of new band, which means, and then you have to fold back all this band back again to this Brilliant zone, which should be smaller because your unit cell becomes larger. And at the end of the Brilliant zone, as Bloch's paper actually told us, that there's a gap opens up. So what you expect here is that this spectrum with the Dirac point here, like this, at some point, at the larger energies correspond to the Brilliant zone edge, will break down into the new band. And basically, this is a new band forms because of this the Moire superlattice that perturb the system, right? So this is basically experimental evidence you can see in the STM. Now, very similar things can be done in the transport. Again, you make the device sitting on the boron nitride. If you just look at this AFM images, you see the Moire pattern. If you choose the right side of the device so that this Moire pattern is about 10 nanometer length scale, that's actually some of the length scale that we can access this band gap or the mini Brilliant zone edges by just choosing different density by just changing the gate voltages. And if you do that, indeed, initially this peak appears at the Dirac point. Also, at the large energies or the large density, corresponding large energies, you have this so-called side peaks appears. And along the side peaks, if you just measure the hole conductivity changes sign, which actually correspond basically, you have this mini bands forms. So it's electron-like band. Here is hole-like band, hole-like band, electron-like band, and those kind of mini band forms from this transport measurement. So we know that if you choose the right set of the Moire superlattice on graphene on the boron nitride, we can create this enough disturbance such that we can form these mini Brilliant zones there, right? So this is very good news because in some sense now we are set to explore the Hofstadter spectrum. How? Apply the magnetic field. So we apply the magnetic field. And once you apply the magnetic field, following experiment can be done. You can measure here's the current going through, you measure the voltage along the current direction. This is what we call the RXX. That voltage you measure divided by current. This resistance is what we call the RXX, longitudinal resistance. Or you can measure the across the current, VXY, divided by current. This is what we call the RXY. So whole resistance, right? And I'm just plotting out here. Because the graphene, we can change the density by just choosing the gate voltage. So this gate will change the density, and this is magnetic field. And you see that there's crazy variations of this RXX and RXY is there. Now, it looks crazy, but there's some pattern appears, like there's some fan appears, starting from this origin, which is near the Dirac point. There's a fan appears. And often this one, for the non-expert, is called the Landau fan diagram, because it looks like fan, right? So that's actually what is expected typically when quantization happens under the Landau level formations and so on. I'm going to go over a little bit of detail. But I want to actually mention that besides those kind of fan that we're supposed to know, there's other structures up here. For example, some side peaks that originally have that's developed own fan, which sounds like the case. But also, there's some features not associated with any of the desired band also there, not originate from here. And also, there's some features that kind of going in parallel of the constant magnetic field. In fact, this becomes even more clear if you just zoom in. Some part is low energy, low magnetic field. Those side fans are constant features. In the features at constant magnetic field becomes quite clear. I would say that this is the evidence of the Hofstadter spectrum. Now, then you say that, well, I don't see any butterfly here. What are you talking about, right? You convinced here? No, probably not. So to make the bit more convincing case, I have to actually step back and teach you how to read this Venn diagram. The way that you can read the Venn diagram, or the reason the Venn diagram is important, especially in quantum Moire effect, is the following. If I just look at the RXX, longitudinal conductance, resistance, I just plotted out fan upside down. Here is my zero magnetic field and high magnetic field and density here. And this black region is where basically you have suppression of the RXX down to 0. If you just look at this plot, cut, this is 0, 0, 0 corresponds to this black spot. And it's coming from the fan. Now, this diagram is nothing to do with the Hofstadter spectrum. This is just a typical device that without any Moire pattern, for example, the measure is something like this. Then what you can do is you can just follow through those kind of fan where the RXX goes to 0. Now, one thing you should remember is that when you get into quantum Moire states, basically two things happen. One is your RXX, longitudinal resistance, goes to 0. In other words, this states that where RXX goes to 0 is correspond to where the quantum Moire states appears. Quantized, the complete quantization of Landau level happens at that density, right? And you can ask that why there's a line. Well, that's basically nothing but, as I mentioned before, it's a relation between the filling fractions. Filling fraction is constant here across this line, which is dictated by both magnetic field and the density. And that relation is related by this one integer number, filling fractions there, right? Why this filling fraction is important? Because, as Streda showed, this filling fraction is nothing but whole conductivity is related with the quantization of whole conductivity. In other words, corresponding whole conductivity, if you just look at this, it's not clear here, but you see that this kind of coupled band. And if you carefully look at this band is exactly quantized in terms of integer number, and that is dictated by this filling fraction nu. And everything's just kind of looking at this fan is clear. Just looking at the slope will give you the value of the RXY. So that's why Venn diagram is important when you study about the quantum Moire effect. Now, arming with this idea, so let's go back to the spectrum, the data that I showed you. So here that I showed the RXX, right? And then what I'm saying here is that there is the fan that I just kind of followed through this one, and that's related with the corresponding RXY in terms of the slope that I can draw in this fan, right? Now let's cut this spectrum, this data into constant magnetic field, one cut. And I showed you both the RXX and RXY here. So RXX goes to 0 many places, and at that time, whenever RXX goes to 0, there is a plateau appears in RXY, and that's basically a signature of a quantum Moire effect. Nothing new here, right? But quantum Moire effect, everything is dictated by the filling fraction nu, right? So at the constant magnetic field, if I convert because the constant magnetic field, if I convert the gate voltage or density in terms of filling fractions, basically I can just rewrite this gate voltage in terms of filling fractions, right? And that actually works here, right? If you look at this, where the nice bands there, basically, whenever you have the 0, there's plateau, and this plateau value is related with basically this filling fraction 2 here. Numerator here appears a 2. Here is a filling fraction of 4. When you have the quantum Moire effect, it's a 4 and appears in numerator. So quantum Moire effect. That idea doesn't work here, though. If you just look at this, filling fraction 4 corresponds to 4 of this numerator there in the plateau, but that actually extended up to the 3, the same value. Now 3 appears in the weird place. Now this one even doesn't correspond to any of the filling fractions. Something is completely messed up in this side, where especially you see that there's a fan does not originate from this 0 appears. So what is going on? That means basically quantum Moire effect is not dictated by the filling fraction. In fact, that's precisely the idea behind of this Diophantine equations, what Wannier actually found, right? In fact, here the quantum Moire effect is controlled by the 2 integer number rather than 1 integer number, right? That's why this filling fraction cannot explain this side. Now the question is then how we can find this 2 integer number out of the data. Well, in fact, that can be done. Look at these figures. Basically, this is magnetic field and this is density, right? If I normalize this figure in terms of the flux per flux quanta, flux per unit cell divided by flux quanta, and this one is a density per unit cell, then this is, we can convert immediately, data can be converted into Wannier plots that I just showed the set of the lines. And now I know that what is in my unit cell because I measured it, right? So simply just replot this in terms of the normalized density and normalized magnetic flux, then I get this plot, right? And there's a lot of structures. Some of them is fan, that typical quantum Moire effect, but some of them are not fan, originate from there. If you just carefully trace all these lines, in fact, you can actually find out that lines correspond to exactly the Diophantine equations that we just described. Slope is exactly an integer number, and offset is exactly fall into this integer number, into this one, so that I can pick up 2 integer number correspond to these quantum states. And if I just make the cut through, that this quantum Hall plateaus actually shows nice quantizations dictated by this slope on these diagrams. So we know that, in fact, we can find that 2 integer numbers that behind of the spectrum. You may not be impressed by just looking at this one, because well, it's complicated structures. You draw the many, many lines. Maybe some of the line hit some things, right? Indeed, if you just look at the zoom in images of the smaller magnetic field range, you can just do the same thing. There are many structures there, but many of the structures can be explained by just drawing the lines. And drawing the lines is not arbitrary lines, but integer slopes with the integer offset in the normalized plot can hit many of the features just we are talking about. Again, you are not convinced, because it's the same thing you can say that, well, there are variety of the structures, draw many lines there, some line will hit. But that's not the case. It's a much stronger statement. Let me show you one thing. Along this line, let me just pick up these 2 lines, right? So this 2 line is picked up where that RXX showed the suppression of 0, and it was not originated from the original fan. And at the same time, when this is suppressing to 0, there's streaks of the plateau value like things appears. What does that mean is if I just kind of plotted out my data along these lines, especially on the RXY, they shows plateau, like the quantum Moire effect. But what is the filling fraction? This is nothing to do with filling fraction. The slope of this line will give you that what is this plateau value should look like. Basically, every lines that I draw, you can just do the same exercise, showing that indeed there's close correlation and there's unambiguous way you can extract these 2 integer numbers, which is behind of the spectrum. You can go beyond this one. I just showed it there's the features running in the constant magnetic field, right? If I just plot it out again in normalized plot, that constant features is exactly lines with this special case, 1/2, 1/3, and 1/5, 1/4, and 1/5 type of this constant magnetic field. There's features, right? And now you start to remember that originally when we present both the Hofstadter spectrums as well as Wannier spectrum, Wannier diagram, there's a special features that reside on simple fractions. That's what you call the fractal band. Basically, that's band, continuous, but near this band, basically there are many fractalized bands that do exist. And in fact, if you just look at whole conductivity, what happens is that because of there so many bands nearby, there's a kind of large fluctuation of the whole conductivity start to shows up as you approach those kind of fractal band. And that's basically sign as well as the sign changes. So that's the kind of feature we are seeing here. But not only that, if I just kind of plot it out, that the cut through the magnetic field at the fixed density. So I just cross kind of many this fractal band across this magnetic field. And whenever I just cross this fractal band, there's a peak appears in the RX, sigma XX, the whole conductivity. More or less is that you can consider in this case the density of state. It's picked up such as I just kind of cross the band. But the important part is whenever I just get the cross there, I get the reversal of the RXY, showing that hole like the state turn into the electron-like states, what it should be across each of the fractal band. But beyond that, if you just look at this, there's some sort of fluctuation like the structure going on. But if you zoom in, that's not the fluctuation. There's a little quantum effect appears in each of these fractal band. What does it mean is, in some sense, your quantum effect itself is kind of recursive across the structures. So showing some of the recursive quantum structures embedded in these structures. So all of these things actually start to show us that indeed we are seeing quite kind of direct evidence that the fractalized spectrums and underlying structures we can pick up from this quantum measurement. And really picking up this integer number, 2 integer number, is quite a kind of exciting things, exciting news we have. Now, seems like already here that it's quite exciting, but you can still mention that, well, I'm not seeing still butterfly here. Well, probably you got the wrong person. I'm just doing the transport. I know that how to measure quantized whole, but to look at the butterfly, you have to just do the energy resolve spectrum measurement, which is not, the transport may not be a good tool. But I would say that visualization is important, but important part here is just kind of rediscovered importance of these 2 integer numbers. And there actually another importance there. There are some things that we can throw in beyond this one. Okay, so up to here that we know that, so we can solve this, or we can just experimentally show that 30 or 37 years old problems, now finally we get to kind of shed some light of the quantizations. But that's actually good and cute problems we solved. But any more things we can learn. Already we see that some of the tantalizing, interesting evidence here. For example, if you look at the energies in the spectrum by just looking at the temperature dependence measurement, it's a bit complicated, but you can just change the temperatures and you can measure the excitations of electron between the gap, and you can just back out what is the energy of each of the states. Turns out that we just kind of plotted out this each of this fractalized gap expressed by the 2 integer number. You can measure the gap, and gap becomes larger and smaller. I just have to present in terms of this bubble diagram. Large bubble is large energy, small bubble is small energies, and so on. It's rather complicated, but important part is there are many bubbles sitting on odd integer number. And this odd integer number is a rather interesting part, because in the graphene, that one thing that I didn't mention during the way is basically there's a more internal degree of freedom than typical case. The spin, and they have this the values that you can put it there, and basically give the electron more degree of freedom, internal degree of freedom you can play around. The net result, I don't have the time to go over detail, is how this internal degree of freedom align them together becomes quite important, especially when you consider interaction between the electron. This becomes really critical because electron interactions form the additional internal degree of freedom spontaneously align in certain structures to form certain the intriguing phase, what we call the quantum Hall ferromagnet phase. And there are many of these different things can be done. And some of the people in this room actually studied a lot, theoretically as well as experimentally. And the whole point here is basically that in this spectrum, seeing these odd numbers with the large energy gap indicating somehow already the spectrum dictate that, or that suggests that electron-electron interaction is rather important in this spectrum, which is not captured by original dark solution, right? pushing this even further, if the graphene quality is better, then you can see that not only just integer quantum Moire effect, you can see the fractional quantum Moire effect. And due to the additional degree of freedom of the electrons that I mentioned, this fractional quantum Moire effect can be slightly different, or it can be substantially different from the fractional quantum Moire effect we know in the gallium arsenide. And even further, now we can actually just do that. This structure of the fractional quantum Moire effect can exist in the periodic potentials, electric potentials, or do they actually change it? That this is kind of interesting questions. It's not only just questions, but now even in the experiment, it starts to show up. Some of this recent data, we have the coexistence of this butterfly, the spectrums, or the fractal spectrums, coexistence with this fractional quantum Moire effect. And indeed, if you just zoom in the structures, some of the the fractional quantum Moire effect strongly affected by this periodic modulation of the potentials and cannot be explained by simple just fractional quantum Moire effect we know without periodic potentials. Supposing that many questions, such as how we can deal with this electron-electron interaction, how we can deal with these composite fermions living in these periodic electric potentials and so on, which is completely undiscussed at this point and can be quite important. Do we need additional quantum numbers? 2, 3? How many quantum numbers we need to describe this electron-electron interaction? I think that's kind of quite exciting problem. All right, I think that's all probably I want to tell you, and thank you for your attention. Not convinced still.
Well, I have to ask them.
Yeah.
I can't. It has nothing to do with the details of your talk, but just when I discovered the mathematical object, it was very exciting because of its intricate structure and the idea that it nested infinitely many levels down. And
right.
So forth. All of that is highly mathematical and beautiful, but I never ever suspected that it might be interesting to anyone in terms of usage, but I read in some of the articles that I saw online that people were thinking that this might have some usefulness, these kinds of this kind of spectrum, fractal spectrum. And do you see that? Is there any way in which it could be useful, or is it just simply a beautiful aesthetic phenomenon?
Let me repeat the question. I think the question is, are there practical applications to these fractional
I think, okay. So,
fractional or right. fractal quantum Hall?
I think that's a very good question, but also very difficult questions. I think in the long range, maybe, because anyways, we are dealing with the kind of exquisite electronic properties there. And we are dealing with various different gaps. And now we can engineer those kind of gaps in some sense. And gaps and electron behaviors, novel electron behaviors is always kind of feeding of the new electronics, new type of the things. But I would say that's really kind of that I can be forced to write some things, then I just mentioned that. In the near term, probably it's not easy to find a good application. Look, this experiment is done extremely low temperature, extremely high magnetic field, 40 Tesla, 45 Tesla, 30 Tesla. We need about 10% of the power that city of the Tallahassee used to attain those kind of the spectrum. So it is very expensive experiment at this point, right? So of course you can say that everything that if sample quality becomes better, we remove the more disorders and so on, it becomes you don't need such high magnetic field and you can just do the relatively low magnetic field. But nevertheless, I think that's bit of the long way to go. I think ultimate goal, we can say that, well, if you understand electrons in this, the unique environments quite well, and if you can engineer, there is some potentials that we can use as electronic devices or magnetic device. But in practice, reaching that, we have many, many others to go through.
I was correct. If you have a question, I have to bring you one. Oh, is that me? Oh, so I just had a simple question.
Yeah.
This is
the experiments are on a well-defined system of a metal with in a magnetic field. Is there any generalization to other systems of incommensurate periodicities? For example, in the things that I love are the rare earth metals have helical magnetic structures which have no relation to the periodicity of the unit cells.
Yeah.
Do they have similar things?
Okay.
There it's one-dimensional.
Right. So I think in some sense, the problem itself is quite abstract problem. So as long as you have this commensurability and commensurability of this two competing length scale, very similar things kind of happens. It doesn't have to be a magnetic field. And Hofstadter's spectrum actually realized some other systems. So for example, magnetic wave that transport through the waveguide with some periodic modulations, you get kind of very similar type of the spectrum. So as long as you have the length scale, that whether you can adjust the commensuration and incommensuration, very similar physics can appear, right? So whether there's this length scale that you can control is an issue of the detail, depends on the detail of the system. Experimentation, of course, they're a lot different, right? I think, for example, the cold dark atom experiment is completely different set of the experiment, although chasing very similar physics behind of that. Yeah, so
question, is there progress in the growth of graphene and creation of superlattices?
Yes, yes, indeed. So although that with the practical region that we still use Scotch tape, there are now other reports appears that you can grow the graphene directly on boron nitride, for example, and they see the very similar things. And of course, the direct growth in the much more well-controlled environment is a way to go, that if you want to get a really, really clean sample. So I'm very hopeful that given that speed of the material growers actually come up with the systems, that I think many of these things can be done relatively mild condition than we can just do now.
Imagine in the near future that we could turn a dial on a device and change the Moire angle continuously without having to prepare a new system every time for a different angle?
That's a bit difficult. But if I have the 10 graduate students, we can produce many different angles.
All right, I'll tell the NSF that that's what you need. If there are no other questions, let's thank Professor Kim again.
Thank you.